Hello, my name is Itzel.
Hi, I'm John.
Hello, my name's Sarek.
Our project is on equilibrium aiding smart insole.
So our project goal for our project is to create a foot pressure insole that provides feedback to the user when they are toe walking. And with this, we are planning on implementing it with several pressure sensors around the insole, around the toe and the heel areas, which you will see in the next few slides. And we will also be planning on implementing machine learning as well. Furthermore, our one of our goals is also to gradually prevent bunions, which are pretty much sores around the feet, which can be very painful when you're walking. Um, and they're the most common within children around the age of 10 and younger, who are the most common to have this problem. And we want this project to become sort of like an influence or a potential solution to that issue in the future. Um, and yeah.
We were planning on doing this in a total of 3 phases. For the first phase, we'll focus on purchasing all the equipment and inventory, which will consist of the featherboard, like the Express and the ADA logger, the sensors, which is the FSR or the force sensitive resistor, and the linear potentiometer, etc. And for phase two, we'll focus more on recording data of various foot positions and be able to detect someone's gait of someone's walking patterns and be able to hopefully correct their walking pattern with a coin motor. And for phase three, we will create an app similar to the app created by Adafruit, which will be able to plot the data stored on the SD card. Next slide.
Progress. So during the month of April, we worked on familiarizing ourselves with our boards and sensors. So we are using the Adafruit Feather NRF 52840 Express board, which does not have a built-in IMU. Therefore, we purchased the ALT IMU-10 version 5 with 6 degrees of freedom. Um, hence, here we had the demo that uses the NRF to read in the IMU's accelerometer and gyro raw values. So as one can see, the raw data mirrors the movement of the IMU.
Okay. And as mentioned previously in our main goal, we will be implementing pressure sensors in our project to help interpret and gather data from the individual. And these two pressure sensors that we'll be using are a force sensitive resistor and a force sensitive linear potentiometer. The difference between the two is one of them, like the force sensitive resistor, only measures pressure, while the other measures pressure as well as the position of wherever that pressure is applied. As you can see to the right of that slide, you can see the overall diagram of how we plan to lay out all of these modules onto the insole. As you can see, we have more FSRs on the toes, since most of the concentration are going to be focused on there. We also have one laid out around the heel, and the linear potentiometer is around the arch of the foot, as well as the MCU on the side. And yeah, that's pretty much our implementation. Next slide. And here are two demos demonstrating the pressure sensors. But prior to the videos, I want to note that in the video it shows that I use the Arduino Uno and besides our board. Um, and because of that, it's pretty much they pretty much have the same IDE, and both sensors are compatible with both boards. But in the future, we are going to be using the NRF 52840 Express featherboard on our actual project. So with the first video, the pressure sensor. Um, so how I programmed it is if you squeeze, depending on how much you squeeze, would transmit values on the monitor. So right now I'm currently putting no pressure on the pressure sensor. And obviously, once I press it down, then the analog readings will increase. Um, and another thing to account for is the LED. And one thing to note for that LED is that initially the LED here is pulled up. So as you can see, it's lighting up right now. But whenever I squeeze, it's going to dim. So a dimmer light indicates more of a bigger squeeze, and a lighter and with no pressure indicates a brighter LED. So here we go. See how that dims when I squeeze. Transitions to big squeeze, and I squeeze it lighter and lighter and lighter on the monitor. And then eventually there's no pressure. Big squeeze on the LED. If I release it, it's gonna get brighter. And I squeeze it, dimmer. For the force sensing linear potentiometer sensor, and this has a resolution in terms of position of 1024 and a resolution for the pressure for each position from 0 to 500. So right now, as you can see on the serial monitor, position at 0 and a pressure is at 0. And obviously, since we're not applying any pressure, we don't indicate any position. So if I were to place my finger right here and apply a little bit of pressure, it's gonna place the position around early 100, or no, late 100s, but pressure is still a little low. And if I squeeze a little bit, it's going to increase almost up to 500. All right, and if I were to move my finger around higher and higher, maybe possibly to the tip right here, we're probably going to get around 1000 as our resolution. And I'm applying a bit of pressure also. And yeah, so moving down would be the same thing. Like here in this middle value, going back down goes it's like around 700, 600, and so on.
Due to not having the coin cell battery required for the RTC or real-time clock to operate on the ADA logger last month, we were not able to do tests and store data on the ADA logger. Luckily, we were able to acquire a battery, and with that, we are able to use a force-sensitive resistor to collect pressure data and store that data into an SD card, which will be displayed on a terminal of the pressure sensor data. We were able to follow a logging sketch provided by Adafruit for logging the data onto the SD card. And we want to stress the importance of storing data onto an SD card because later in our project, we will be collecting data from multiple sensors, and there will be a large amount of this data that will be needed to transmit it somehow. And this will not be able to be done through Bluetooth because the sheer amount of data that we'll need to transmit. So the only option will be transmitting the data locally, and that is through a SD card, which we luckily are able to test with the ADA logger. Next slide. This is the schematic of how we were able to collect the data that was acquired by the NRF52 Express, which is the blue board on the left side, and the ADA logger, which is the black board on the right side. And the FSR is the pressure sensor that is shown on the breadboard. Next slide. Here's a video of the demo. Here's the NRF52 Express and the ADA logger, and on the breadboard is the FSR, which is the force-sensitive resistor. And basically, the Express is going to collect the data from the FSR, which is going to be stored onto the SD card, and as the pressure is being detected by the FSR, the data is going to be displayed on the terminal, which is being stored onto the SD card.
A start in machine learning. This is the first time any of us are using machine learning with a microcontroller. Hence, we use this tutorial to help us with understand how to implement TensorFlow on the NRF board. This tutorial is called the Magic Wand. It interprets raw accelerometer data to identify gestures. In this case, a wing, a ring, and a slope. They use 150 examples of each gesture to train the model. The code differentiates between the gestures without using a lot of data because there is less variation in the expected inputs, hence make it easier to train. As we implemented this code, we had to make a few adjustments so that it works with our board. So here are the 3 gestures: the wing, the ring, and the slope. And this is the demo. And as you can see, that is the slope and the ring. And the wing. So as one saw, based on my hand gestures, the following results were generated: the slope, the ring, and the wing. This leads us to future work. Now that we have all our sensors, we will start setting them up in an insel for data collecting. We will use the magic wand example as a template. For our project, we will collect data using an actuator and a prosthetic foot supplied by Dr. Benke. The data logger will then save the data in which we'll use to train our model. We will collect data in the walking positions demonstrated in the image. That is these. This example code uses a convolutional neural network in which we'll adjust to our project to differentiate walking movements. At the very end, provide feedback to the user. And that's it. If you have any questions or concerns, please email us, and thank you.